I love the previous talk because it gave a great big picture view of the current situation. So historically, design have moved to computers. So like probably you know that now cars, planes, and boats, every macro object is designed on a computer. Even art is done on a computer. But at the atomic scale, it's still so difficult to understand what's going on and to simulate that we don't have quite the tools yet to be as efficient as at the macro scale. So I would like to argue that one of the big bottlenecks is actually the human brain. We're not smart enough now anymore to understand everything, and we need different expertises like in biology, physics, chemistry, computer science, quantum computing, algorithms, high performance computing. It's so hard now that nobody can do it alone. And so we would need to assemble different fields, different expertises, like the Avengers. We need to assemble forces to federate people and to work together. So we tried to approach that from a computer science point of view, because we were computer scientists in a French computer science lab. And what we did was develop a platform that's open called Samson. So Samson is for software for adaptive modeling and simulation of nanosystems. Works in French as well, probably Italian, Latin languages, like système adaptatif pour la modélisation et la simulation d'objets nanoscopiques. I'm sure it could work in other languages. So the idea is that since nobody can do everything, we have to have a core that makes it possible for experts to connect their expertise. So we want to make it easy for computer scientists to add their expert algorithms inside. We want to make it easy for physicists to add force fields and algorithms that will predict whether a drug binds to a protein or whether material will self-assemble. We need to make it easy for data scientists to take experimental data and use this data to train models. We need then to make these models to be easily usable by others. We need to be able to design objects that combine fields. So for example, there is a great technology, a great recent technology of COVID sensor, which was done thanks to the combination of different disciplines. So basically what they did is they took some graphene, and graphene conducts electricity. On this graphene, they attached antibodies thanks to linkers, and these antibodies are specific to spike proteins. And the way these sensors work is that you make a current go through the graphene sheet, and in the presence of the spike protein, the current is conducted differently in the device. But to design these things, first, you probably need to be a great physicist, but you need to combine different things. You need to combine electronics, material science, biology, physics, industrial production, because now they need to build these devices at scale. And so what we try to do is make a software that has a core with some core functionality and especially extensions. So you have a software development kit that people can use to build new extensions depending on their fields. So there are some plugins for like DNA nanotech, some plugin for science communication, doing animation, some plugin for materials, some plugin for drug design, etc., etc. The thing is that you can then pipeline these and combine everything. So I'm just going to do a quick demo of this. So this is how it looks. It's basically like a CAD application. It's basically like a CAD application, but for at the molecular scale. And it's integrated in the sense that your extensions, your force fields, your apps, your editors are all integrated in the platform, and the interface is built automatically based on your extensions, either the ones that you got from the platform, from the marketplace, many are free, or the ones that you develop yourself. So for example, one of the first things that you want to do when you look at a molecular model is just to simplify the way you look at it. For example, so over the years, many people have invented many different ways to represent molecules. So this would be the default basic way where you represent atoms with bonds, atoms with spheres and bonds, molecular bonds, even though this is a drastic simplification of the physics interactions that result in from the Schrödinger equation or direct equation. So this would be a simple way. But so color code, red is oxygen, gray is carbon, blue is nitrogen, and white is hydrogen. But over the years, since potentially you can have many different, many atoms in the system, even this is not that simple to understand. People have invented other visual representations. So here are a few of them. Here, for example, you could decide that you don't represent the spheres just because you want to see the linear structure. Or you would decide that you only represent spheres, but with a radius of the actual size, the actual approximate size, the van der Waals radius that the atoms are going to take. Or you would look at what's called a secondary structure to see the overall general assembly of the atoms. For example, we know that in proteins, locally, some amino acids like to fold into helices. So this was a representation that was created, I think, by Professor Anderson in the US in the 50s or in the 40s, where people decided that it's much simpler to look at this tertiary structure or secondary structure locally, the helices, the beta folds, instead of the atoms. And then other people decided that, well, it's fine also to look at the different types of surfaces, molecular surfaces. And so you have Gaussian surfaces and solvent accessible surfaces where the water can go, or the solvent excluded surfaces like here, where the solvent cannot go, because this might be useful to know where a drug might bind into a protein, etc. So that's the first thing that you want to do, is you want to look at, you want to visualize, and this has to be open as well, because potentially a computer graphics PhD student or researcher is going to invent new representations. And there are some people who created new visual representations for DNA, because you have so many atoms that you need multi-level graphics depictions of DNA to make it easier to deal with, again, because of the human brain bottleneck. Then potentially you want to communicate your results. You want to communicate science, either to your colleagues or to general public. So we made a way to easily create animations and presentations inside something. For example, here I have the protease of HIV, and this was one of the first successfully designed drugs in silico. So here I have an animation where, so it's not a physical process, it's just an animation process, but it's to show where the ligands bind in the protease of the HIV protease. So by the way, this is a very interesting biological mechanism. This protease is part of the replication mechanism of HIV. And the way it works is you have these binding fingers here, which open and close. So it acts like scissors, it's an enzyme. And when a chain goes inside, it cuts the chain, and then the cut part reassemble to form another part of another virus particle. So it's part of the replication mechanism, and the idea of making drugs that bind inside this active site of the protein, the whole idea is to block this replication mechanism. So you need to be able to communicate science and make animations, movies, potentially watch this in VR. We have modules for VR as well. But then, of course, you need to be able to design new objects, like people here who design DNA self-assemblies or who do protein design. And you have many ways to build things. Potentially, you could start from atoms. So you would say, well, I add atoms progressively, and I'm going to build a chain here. Or I could add bricks. So it's a bit like computer games, you know, when the game tells you if here it's allowed or not, like, because you don't have enough space. But one thing with atomistic design, molecular design, is that very rapidly you can create something that's completely unrealistic. Like, unlike what we do at the micro scale, like let's say you design a car, you have a lot of choice in the shape of the car, and that's why we have so many different shapes of cars. We have lots of different shapes of molecules, but the idea is that you can kind of separate the modeling from the simulation, because anyway, the metal or the plastic will make it so that it will hold together. Here, I could try to take this atom, these atoms, and move them here, but it's actually not realistic. Okay. So very rapidly, I need to include physics inside to make sure that I have something at least a bit plausible. So I can just minimize the potential energy of the system and simulate the interactions with an approximation of the Schrödinger equation to make it so that I have at least a local energy minimum and a structure that's not completely unrealistic, and that would at least hold together. And I can make that on different objects. And so that's one way to build something by assembling things. So it's not because we're able to build it in a computer that we would be able to build it in real life, of course. But for that, there are also people working on algorithms that try to predict the reactions, the set of reactions that can be used, potentially by combining, by developing extensions that pilot robots, actually. Another way to build things is to build them procedurally, meaning instead of explicitly saying where atoms are, you say the macro parameters like the size of the objects. For example, you could say that you build a nanotube by drawing its extremities and then choosing the radius and the n and m parameters of a nanotube. Meaning, so you build a nanotube by taking a graphene sheet and folding it, but depending on how you fold it, how you attach it, it has different properties. So you could create that and then decide to study its elasticity, bend it, etc., etc. So this is a second way to build procedurally some objects. But then another way, of course, more and more popular way, is to design through AI. So you mentioned AlphaFold, and there is now this revolution of protein folding algorithms, and there are many. So there is AlphaFold, OpenFold, OmegaFold, ESMFold. So recently, which one?
You don't have that. I mean, the problem with these social the problem with all of these is like AlphaFold is great, but it's only great for what it already knew. So I would never use AlphaFold.
Exactly.
I would never use it if I was a scientist. I would use it if the proteins I'm playing with are unknown. If the proteins I'm playing with are small deviations, then fine.
Exactly. So that's one of the very good use cases. Like I said, right now with COVID, we have variants. And one way to study the folding of these variants, the impact on the structure, and whether it's plausible or not, that here there will be a variant because this amino acid will mutate. This is one strong use case. Yeah. So in pharma, some people are wary the risks of AlphaFold, but still they're very excited.
But sure, but you just use it's AlphaFold is a gimmick, right? It works very well. It's like saying, hey, neural network, we can move on from that. We don't. I mean,
it's just a step.
It's not a revolution. What the revolution was protein crystallography and the PDB database. That was a real revolution. Using a regression and algorithm to basically connect one to the other is not a revolution. That's known for like 100 years.
Yeah, I don't agree with that at all.
Well, I know, but you're wrong.
Yeah, I think you are.
We can debate on later.
It's a bit like crystallography, so because it's just a virtual microscope. But
you're doing mathematical regression. That's what you're doing.
No.
Crystallography is not a microscope. You're solving.
There are so many different technologies in these models.
And you solve yourself.
No.
I have many hundreds.
Okay. Have you solved a machine learning model?
Yes.
Have you developed them? But difficult ones.
There's more variation in proteins.
Yeah, it's so.
There's more variation in the protein.
I think,
plastic.
anyway, let's go on. I'm more
Any-
interested in what you said.
Anyway, in a sense, I'm not pro AlphaFold. So right now we're developing a plugin to integrate AlphaFold, but we actually already integrated ESMFold. So I don't know if you've heard about ESMFold. So the one by Meta, which is much faster than AlphaFold. So it was so fast that we integrated it. And because again, our goal is not to reinvent the wheel we just want to create an ecosystem that people can use these methods easily and then can compare them. So, and then potentially you decide that they're not worth it, but at least people should have access to them and be able to compare them.
No, your point is good. I think having the hub to connect it all together, it makes a great deal of sense. But I'm just saying, beware of the hype. That's all.
No, sure. Same with quantum computing.
Well, quantum computing is never going to work for a very good reason. So let's not go there unless you can solve in the many worlds.
So this is a small protein.
It's actually the one I was showing earlier on different visual representations. This is its sequence. And this is ESMFold, so the meta algorithm integrated inside Samsung. So I just paste the sequence, and the way it works, I just click predict and import. Hopefully the network will be good enough, yes. And it gives me the structure, the prediction. And you see it's rather close to the one on. And actually the confidence score is visually represented by colors. So blue means like the algorithm trusts its prediction. But what's nice with that is that I can try to modify and make variants of that and see if it has an impact. So let's say it's cold here. So I say blah, blah, blah. I just predict this consequence and it unfolds. So this is a silly example, of course, but this is one way to use prediction, because yes, potentially far from the database on which it has been trained, it's incorrect. It's not transferable. We don't know. It's not sure. It might be, but
This is a strong use case.
That's a very fundamental and different question. I've been seeing the chemical computing advancing in these ways, and it's often biology, proteins, these very well understood things. There's a different class of problems. I was working on geologic carbon sequestration, and here we have problems. We've got problems of you've got very complex clay and earth minerals surface chemistry, and they have three-dimensional structures. And there's different surface properties as well, these different crystal minerals that when we say a clay or a rock, what we actually need is a soup of 30 different things with a very complex physical structure.
Yeah.
Well, how that's laid out tells you, did you get this many barrels of oil out or this many barrels of oil out? Equivalently, how much CO2 do I get out? And you can have factors of 2 or 3 differences, which have factors of 2 or 3 differences in cost. That world doesn't think this way. It's in some of them do. Some of them at Berkeley, at things like this, are looking at like fundamental chemistry, and there's this upscaling problem. And so I see that you're making immense predictive computational chemistry within, like you said, there's a bounds of how far you can stretch it. But there's these bigger problems. There's these very other sets of problems. They're also chemistry. So some of it's organic chemistry, but it's still chemistry. Do you see this world of the biological chemical computing moving over into things like earth sciences, physical property computing, and multi-phase flow computing?
yeah, I think it's a matter of scale, as you described briefly. So some people actually like Michael do coarse grain calculations and statistical calculations. So you need ways to do multi-level computing.
I'm not asking about multi-scale. I understand multi-scale. I've published about it. I understand that. I'm asking something very different. The biology people, polymer people, the materials people who do real manufacturing, the chemical engineering people, and the earth sciences people never talk.
Oh, but that's our goal. That's how we try to help. We want to make one way to connect them. And
I was working on the BP oil spill. It turns out there's viruses and funguses that live on the gas bubbles that go up 1 kilometer. And this is really important for ocean biology. And we basically know that we have no clue.
Yeah.
99.9% we have no freaking clue.
Yeah.
The gas bubbles rise in the ocean. It moves the biology. There's a huge amount of chemistry, physical chemistry, salts, water, gas, oil, but then there's all this biology that's also happening. You don't think about it. And no one ever thinks to even ask do this kind of work.
That's the thing. Yeah, we need a way to, and I mean, I really think it's same as a conspiracy theory. It's like limitations on the human brain that make it so that we have specialized over the years and we don't speak to each other anymore. And we need a way to have a common language, to have a common way to integrate the different works of everybody. So that then people will say, well, if you want, you can exchange data, exchange algorithms, and have a common language to talk to people.
You see these kinds of, you have a very good open platform that's smart about how to bring in people from different areas. Do you see like different adjacent open platforms in polymer science or something? Like the guys, people who make plastics for a living, they must have a similar computer system.
Sure. I mean, there are some software competitors, but they have a different structure and different business model.
Yours is good because I mean, you know robotics, right? They're trying this sort of stuff, but having it open is so much easier because then people can trust what they're putting in, right? Black box, broken loop, black box. It's not going to work. Yeah, that's good. Yeah. So, can you put physical properties data into this?
So, what scale of properties?
Just so you could just measure, say, I don't know, just put in a molecule and calculate its UV spectrum, and you could then put it into UV spectrum or something like this, or calculate its NMR spectrum.
I mean, I guess if you have a function that's computable from atomic structures, then you can program it. Then potentially it's so there was a very interesting discussion about the length of the calculations. And I don't think it's a big deal because it's the same at the macro scale. When you simulate a crash test in a car, it's gonna be very fast, but if you want to do it with finite elements, it's gonna take a long time. When you simulate the airflow on a plane, it happens in real time, but it takes also a lot of time to do it, and it's fine. And I think the reason it's fine is that if you train an algorithm once, you can copy paste it to everything. And I think people don't realize the big deal with self-driving cars, for example. We humans, we have to learn each of us one by one how to drive. But if you train one algorithm good enough, well enough, then you copy paste the algorithm in the cars. And that's the revolution. And we can't do that on the brain. And so that's why I don't think it's a big deal that it's slow to compute things. Yes, it can be slow, but we do it once.
I would highly disagree with you, though.
On the cars or
on the computability issue, because the problem with the current models is that you need to be highly trained to use them.
Sure.
And in that way, the copy pasting is actually not solving anything new.
But we won't always need novelty. Like once a problem is solved, it's solved. Like maybe one day we will solve the problem of carbon capture. We don't need to solve it 10 times. We need a good solution.
When nature solved it once, with Rubisco, there seems to be no other way right now, which is scary, which is why we're thinking.
We actually, so my PhD advisor invented pulling CO2 out of the atmosphere and shoving it into rocks. There will be 10 solutions and your tools will come into play. The reason is that we'll have 100 different process conditions that we need to be capturing by the CO2. And so different process conditions have different chemical thermodynamics, different fluid flows, different materials compatibility. Am I at 600 degrees Celsius in the process? And so I want a molten carbon to get the CO2 out. Am I at ambient temperature and very low dilute CO2? So you end up with a class of entirely different classes of chemistries. And then you have your kinds of things where you say, I want to weakly bind CO2 with an ionic membrane or something. How do I tweak the membrane? Your tools absolutely come into play. Very, very important for these things. So there will be 100 answers, and your tools will answer how to optimize a number of those classes. It's very, very useful.
But maybe we're playing a bit on words because
you're changing the problem. You're saying, well, sure, we'll have one problem, but that will change a bit the parameters, and I would say it's a different problem, or it's a class of problems. And so, but still, if we have a class of problems and then we find the class of solution, then we move on to something else.
So I think that's where those 2 points kind of converge, which is and where I would anticipate this kind of needs to go. It's basically, from my perspective as well, from work I've done, is usability for a non-expert, basically like computer whiz, to model non-covalent interactions at scale. And that goes for any system. And then that's our whole point of, because that can be from, whether it be, you know, I don't know, say a virus binding to a detector of some sort, or, I mean, we have a classic issue here of, or a real issue of, for example, self-assembly of what would say is non-classical amplifiers. So something that doesn't conform to the ability to basically calculate a critical packing parameter. This is all around like nanomaterial based stuff. We just don't know how to do it. So if we could basically put that in a simulation at scale, but that's not.
No, and I'm not saying that it's solved at all. I mean, our goal is just to ease a bit the collaboration.
And what I think, and that's why this is a great starting point.
Yeah.
But and I would anticipate. So my question was actually going to be in terms of like, can you export this into anything, a tool that you know of that can do those kind of basically looking at. So say, you know, you could put in your nanotube and a bunch of peptides, for example, or whatever, and then I presume in your software it can't calculate all the energies of the interactions, or can it? Or do you have to output and
That would be an extension.
Yeah.
So actually, the Adenita extension was developed by the university in Austria to do DNA multi-level modeling of DNA, and it can communicate with Kando.
And it looks like a pretty relatively easy user base to navigate, by the way.
Yes, you download it? Thank you. Your user number 2.
I somehow doubt that.
Everybody start downloading now. Come on.
So do you get biologists and teach them computers, or do you take computer people and teach them biology? Or you have to sit together for a long time?
I mean, for the core, I mean, we just work on the core. Like we work a lot with other people, like the experts.
But are you computer people who learn biology, or are you biology people who learn computers?
Yeah. Well, as I don't know if you know the French system. There's a engineering school called Polytechnique where you do a bit of this, a bit of that. Okay, so yeah, but it's mostly computer science.
Roman times were a long time ago.
How does it work with getting data sets into the software? Like if you wanted to, let's say you have a affinity prediction model or something, which like those cannot really do well, so you use data sets in your lab, and then you want to upload that or training model on the platform. Or like, how do you see this?
Then what would you do with the data set? You would predict something or
Exactly,
something
you train a
else?
machine learning model, and then basically there on the right side, I see from here like a lot of icons, and you use model XY to then predict how this. To your question, just left nanotubes, like maybe the kind of like chemical potential computation is not as good, but someone has like done a bunch of experiments and has a better model, which is not physical.
So that's a great question, because that's one of the directions that we want to work on. Make it easy to integrate these data sets. At the moment, it's done on a per extension basis. Like you would develop an extension specific for your use case, which takes a CSV file, and then
but because that's also what we've seen, that like just progress in models is so fast, and there's new models for protein engineering coming out every week.
Exactly.
Basically, if you have this open platform, it's like Hugging Face for whatever chemical.
thank you. That's exactly that. So imagine Hugging Face for molecular design. That's what we want to do.
Well, thank you very much.
Thank you.
Thank you.
Thank you for the question.